Okay, here we go. Any questions before we get started? Zoomers? Are everybody good to go? Excellent. Roomers? We're fine? Okay, good. Turn the clicker on. Here we go. We're going to combine both differentiation and integration into one lesson today for exponential functions. In particular, we're going to look at e. Does anybody remember, without looking at your notes, the number for e?
2 point.
You think you can do it? Go ahead.
2.20, and then it was like there was 1828, 1828. That's all I remember.
You missed a 7 in there.
Oh, excuse me.
Because he was the 7th president of the United States, 1828, 1828, 45, 90, 45.
Okay.
Okay, good, not bad. All right, so talking about E. Today we're going to talk about the properties of E. We're going to find the derivative. We're going to find the integral, both of which are ridiculously simple. So simple it's almost embarrassing. And then, of course, you should be kind whenever possible, and it is always possible. Anybody know who said that?
No.
You. I just did, yes. But who? Let me rephrase my question. Who said that quote originally?
Dalai Lama.
Very nice, the Dalai Lama. Okay. Let's start with this. What is the natural log of e to the x? Anybody? X. Whoops. Let's try that again. Let's try that again. There we go. I don't know how to use my own board. Did you say that, Kev?
Yeah.
Why?
Because you would take the x up to the front, so it'd be x times natural log of e, and natural log of e is 1, so it's just kind of 1.
And seeing as you're probably pretty good at how this whole thing works, what do you think e to the natural log of x is?
Well, you would take the natural log of x, put it to the front. Wait, I don't know.
What do you think it's going to be?
1.
Good guess. Nope.
X again.
It's x.
Oh.
Okay, what does that mean? If I put e to the x in the natural log and I get x, and then I put the natural log of x into e to the x, and they both give me x, what does that tell you about e to the x and the natural log function?
They're inverse.
Bingo. They're inverses of each other. Okay, that's what we did 2 days ago. Okay, so thank you very much. Easy peasy. Which means they're reflections of each other over the line y equals x. I did not include the line in there, but I assume that you would see that. Nothing fancy schmancy there. Okay, good. Little bit of pre-calc review. How do I solve that equation? Notice I asked the question, how do I solve it, not what the answer is. Okay,
Don't you make it a natural log?
beautiful. So when you say that, do you convert to log form, or do you use the natural log of both sides trick?
Convert to log form.
Okay, so what would that be in log form?
Natural log base b of 7 equals x plus 1.
Well, okay. Yes, I'm just going to tweak your verbiage a little bit. Natural log base e is a redundancy,
Okay.
because log base e is the natural log. So the natural log of what now?
7 equals x plus 1.
Okay, good. So converting between log form and exponential form and log form. So natural log of 7 minus 1 is equal to x. Can somebody put that in a calculator and tell me what that equals, please?
Natural log of 7 minus 1.
Yes, sir.
0.459.
right, we'll go with that. Can somebody confirm? Not that we don't trust Kevin, but
Sorry.
he's kind of shifty.
0.945.
0.9459. There's a 9 here.
Yeah.
Okay, there we go.
Yeah, I got the same.
Okay. Some of you may have learned a different method to solve this, and that is the natural log of both sides trick. Basic rule of algebra. Whatever you do to one side of the equation, you have to do to the other side of the equation. Which, after one step, gets us exactly where Kaylee was, and that is the natural log of e to the anything, like Kevin said earlier. Bring the x plus 1 out in front, and we get x plus 1, and the rest makes perfect sense. Either method is okay with me. I don't care. I will say that many people screw up converting to exponential or logarithmic form. So I find that a majority of people prefer the natural log of both sides trick. But either one gets you to the same results. Okay, so again, more pre-calc stuff. Oh, I think I actually have, yeah, there we go. Oh, look, I worked it out. And then, there we go. Beautiful. Okay. A little information about e to the x. Just for graphing purposes and for discussion purposes, you notice that its domain is all reals. If we go back to the picture that I had here, here, you can pretty much see what I'm showing you on that other slide. Its domain is all reals. It continues on to negative infinity and to positive infinity. It has a range of 0 to infinity. It starts at the x-axis. It's asymptotic to the x-axis, meaning it never touches the x-axis, but gets very close. It passes through the point 0, 1. If the natural log function passes through the point 1, 0, then the exponential function will pass through the point 0, 1, because it's a reflection. Blah, 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 blah. What else we got here? There we go. Always increasing. It's 1 to 1. It's concave up. And the limits, if you look at the graph, you could see those limits would make sense. As you go very far to the left, it's going to reach 0. And if you go very far to the right, it's going to continue going up and up and up and up to get infinity. Okay. All right, here we go. Derivative. This is fun. I love this lesson. Okay, so I want to figure out what the derivative of e to the x is. To do that, I'm going to use logarithmic differentiation. So I'm going to start over with y equals e to the x, and I'm going to figure out what the derivative of e to the x is. So refreshing your memory on this, we take the natural log of both sides. We use our log properties. Kev, what's the natural log of e? 1. So we take the derivative, y prime over y equals, well, that is going to become 1. So that's the x. Okay, we're good. Hold on. So therefore, y prime is equal to y. What does that mean? Well, A, I screwed up. Or B, what does that mean? Anybody?
But where did the x go?
What's a derivative of x?
Oh,
Yeah, so notice in this step I took derivatives here. Good question. What's y?
E to the x.
Oh! Hannah, you look perplexed. Perplexed. I couldn't say that with my mask on. Perplexed. What's bothering you?
It's kind of weird.
I'm weird. This is weird or I'm weird?
Oh, that's weird.
That, okay, good cover. Yeah. Why is it weird?
It's just if y is equal to. Okay. Sorry, I'm like.
That's okay. Anybody else? What's bothering Hannah? Or what's bothering you about this? Or is nothing bothering you? Are we good to go?
They're equal to the same thing.
How can the function equal, the original function equal the derivative?
Good. Is that what you said?
Yeah.
Yeah. It's its own derivative. Mind blown. Yes. It's one of the few, if not only function, that when you take the derivative, it's its own derivative. The derivative of e to the x is e to the x. Well, that shouldn't happen, but it does. And then number 2 is thrown in there just for good measure, because you know that I'm not going to ask you to just find the derivative of e to the x, because that's ridiculous. I could teach a chimp to do that. I'm going to make it more interesting and put it as a function. E to the something else. So the key is remembering that it's itself with a chain. Nothing fancy there. You just got to remember to chain on the derivative of that exponent. Don't overcomplicate this. The derivative of e to the u is itself times the chain. Shall we look at an example?
How is that different from number 1, though? Like, would you have to just chain on?
Excellent point, Max. I gave you both of them, but I never think of it as two different things. I always consider the first one just like number 2, because the derivative of x is just 1. So if I see e to the anything, I always see the derivative as that thing I started with the derivative of the anything. But some people like it broken into just e to the x and then e to the u. Okay, so again, KISS method. Itself times 2. Done. Are we all good with where the 2 came from? Yeah. Okay, good. Let's move on then. Geez, swear it's Friday. What's the matter?
It's been a long day already. Wait, actually, I'm not okay with where the 2 came from.
There's nothing wrong with asking that. It's a derivative of 2x minus 1.
Got it.
Okay?
Didn't know that.
All right. Chew on that for a second before I just tell you the answer. Find the derivative. Bella, could you help me out, please? What's the derivative?
Well, first you start off with like rewriting the e to the negative 3 over x.
Love it.
And then would it be like times, I don't know, negative, or times 3 over x squared?
Bingo. Perfect. Now, not everybody may have followed you on that 3 over x squared. Could you explain that a little bit, please?
Well, I just did the derivative of negative 3 over x, which is like the same as negative 3 times, x to the negative 1. And then you do like the little exponent rule thing. And yeah.
Good explanation. Love it. Okay. Anything tricky about that? No? Good. That's why I told you you'd like this lesson. It's easy. Okay, so before I even click on the next slide, tell me what the integral of e to the x is. E to the x. If it's its own derivative, it's going to be its own integral. Sure enough. Okay, common mistake. Does that statement make sense? This has to be done as a UDU. And in fact, we don't know, oh, we can do that. Yes, we can do that. But it has to be done as a UDU problem because we have a function inside a function. Composite functions have to be done as a UDU. So how do you do this? U would be equal to 2x minus 1. du is equal to 2 dx. So dx is equal to 1/2 du, which means we would get 1/2 times e to the 2x minus 1 plus c. And that's a big jump. Hopefully you followed me there because what I did is I said, okay, well, this is 1/2 times the integral e to the u du. The integral of e to the u is itself. Plug it back in. You got the 1/2 in front. So what commonly happens in these types of problems is we lose that 1/2 if you don't do it as a UDU problem. So please do it as a UDU problem. Now I just did that. I'm almost sure I have an example on the next slide. Okay, so we'll skip it. Okay. But hold on, I'm not going to skip it. If you're good at pattern recognition, if you're following what I'm talking about, you should be able to fire this off right away. The answer would be 1/3 e to the 3x plus 1 plus c. Now, how did I do that? Well, because I've been doing this for a while, but also based on the pattern that we saw in this guy, taking the derivative of that linear term is going to give me a constant. You take the reciprocal of that constant, and we end up with that puppy. Okay? We're done. By the way, that's called the Batman function. It's an actual mathematical function that when you graph it, it will give you the bat symbol. I don't know what it is, but it exists. You could search it on the Google. Well, oh God, I hate smart kids. Yes, you're right. That's my fault. That's the Batman equation.
Thank you.
That was nerdalicious, Josie. Does not pass the horizontal line test, therefore its inverse would also not be a function. That was me mocking you, by the way. Oh, it was Hannah that said it? I'm sorry, I thought I'm laying into Josie. It's actually Hannah that said it. Okay. Questions from you bums at home? No? Good. Let's then proceed.